So this lesson's over molarity. We're actually going to be using a formula from the back of your formula card. So make sure that on the back of your formula cards you can locate this formula when I show it to you. Now molarity is represented by the variable big M. It's a capital M, so I'll always refer to it as big M. Make sure not to represent it as a lowercase m because lowercase m actually stands for mass, and we want to make sure that we have our variables straight. Let me just tell you what molarity means. Molarity is the number of moles of solute dissolved per liter of solution. It's basically a concentration. You might have noticed through our labs, some of the brown bottles were labeled as 1M, 0.5M, 2M, 3M, and those capital M's represent the concentration. How many moles of solute are dissolved per liter of solution. So it's just a very specific type of concentration. So just to give you an overview, a big number, a larger value, numerical value, means that it's more concentrated, it's more solutes dissolved. A smaller number means it's less concentrated, less solutes dissolved. So if you try to think about which solution is stronger, it's going to be the one with the larger number. If you ever see an acid marked in our lab with 6M on it, that's much more dangerous than an acid labeled 1M. So just for future reference. We call molarity a molar concentration, and we are talking about the same moles as the whole school year we've been talking about moles. So molar concentration, whenever you read it out loud, so if the bottle says 3M on it, we read it as 3 molar. That's just how to read it verbally, verbalize it. And a 2 molar solution is, a 2M solution is read as 2 molar. That's just an example. The volume involved is the total volume of the solution. That includes the solute inside of it. And I'll show you later on the slideshow how to actually create these solutions using a volumetric flask. Here's the formula for molarity. We have big M, molarity equals moles of solute over liter of solution over the liter of solution. So I actually think that this formula is good for those of you who aren't very good at algebra. I've noticed through my years of teaching that you guys pretty much rock cross multiplication, but if it's not a cross multiplication problem, sometimes we have some difficulties solving the problem algebraically. And so if you set your M over 1, it now creates a cross multiplication problem, and it makes it a lot easier to decide, do I multiply or do I divide? Now here's something to know. A red flag should go up anytime you see grams or mass. That means we're not just using one formula, but we're also going to be doing some side work. So watch out for that throughout the PowerPoint. If we ever see grams or mass, we're going to need to do some side work. So grams are really important because in the actual lab, when you're doing a lab assignment, you can only manipulate grams. You can only put things on a balance and measure grams, but you can't measure moles. Although we use moles because it's a more practical unit, moles is not something that's tangible. We can't have a balance that has moles, so we have to do some side work, some conversions to help us convert to and from moles and grams. And just remember, molar mass can be determined by looking at your periodic table and adding up the masses of each of the individual elements. So we will see lots of problems that are related to this concept, but just remember, anytime you see grams, a red flag goes up. This is how to actually prepare a real solution. So if I were to ask you to create a solution, what you would need to do is you would need to add 1 mole of solute to a volumetric flask. A volumetric flask is, I'll show you on the next slide, has a very, very long neck with like a round bottom. We're going to add about 1/4 of the flask of distilled water, swirl it around to make the solute dissolve, and then finally you keep adding water until it reads at the 1 liter mark. Here's a visual for that. This is a volumetric flask. The reason it's shaped this way is so that you can swirl it around by holding it by the neck and just swirling it, and everything in the bottom gets mixed up together. Sometimes if you have like a graduated cylinder, it's not as easy to mix things around or it'll spill out the top. So that's the reason it's designed this way. So if you were going to create a 1 molar NaCl solution, you would measure out 1 mole of NaCl, and to get this number, you would look at your periodic table. You'd find the mass of Na, 22.990. You'd add it to the mass of chlorine, 35.453. Those are numbers from the periodic table, and you get 58.44 grams. So you're going to measure that out using your balance and then add it into the volumetric flask. Once you add it to the volumetric flask, you add a little bit of water, distilled water. We want the pure stuff, and then you swirl it around. Once you're finished swirling it around, it's all mixed, you're going to basically dilute it to the mark, and that little line there represents 1 liter, and now you have a 1 molar solution, and that's how to create a solution. When it comes to molarity, can be solved using a simple formula. So let's start off with this. One of the things, let's just go ahead and start. We always want to start off with the formula big M, and I always put this over 1 because it makes it easier to solve algebraically. So big M over 1 equals moles over liters. And what we're going to do is we're just going to basically plug in our numbers from the problem. We have a molarity of solution. It contains 0.80 moles, so I'm going to take 0.80 moles and substitute it for moles. And make sure not to call molarity MOL or call moles M, because you can see how they can be easily mixed up if you use the wrong abbreviation. We have 50 milliliters of solution, and milliliters is not the unit we need to use for the denominator. Molarity always needs to be solved in liters, so we are going to convert that into liters. We can do some side work using dimensional analysis, or we can simply move our decimal place to the left 1, 2, 3 times, and that's where I got 0.050 liters. Again, this is equivalent to 50 milliliters, so if this is 50 milliliters, my decimal point would be right here. To convert it to liters, I can just move my decimal point over 1, 2, 3 times, because the denominator always needs to be liters. That's just the formula for molarity. Now we can go ahead and solve the problem. You can go ahead and just divide these two, 0.80 divided by 0.050 to get molarity, or you can use cross multiplication and it comes out the same way. 0.80 times 1 divided by 0.050, and we have a final answer of 16 molar. 16 molar. I did show my answer here with 2 sig figs because both of my numbers here have 2 sig figs. Next problem, how many grams of NaCl are needed to make 5.00 liters of a 0.3 molar solution? With this problem, red flag, we see grams. And with grams, what we are going to do is we are going to need to do some side work. But what we need to do first is use our molarity formula. Here's our molarity formula, and I have it set over big M over 1 equals moles over liters. I'm going to plug in all the numbers I have, so I'm going to take the liters and I'm going to take the molarity and put it in the molarity position. I'm going to take the liter value, the volume, and I'm going to put it in the denominator position. And now I see I do not have moles. So I'm going to go ahead and solve for it. I can use cross multiplication and do 0.3 times 5 divided by 1. 0.3 times 5 divided by 1 to get 1.5 moles. This is not the end of the problem because the problem is asking us for grams. This is 1.5 moles of NaCl, and all we need to do is a side conversion to convert 1.50 moles into grams. So you're going to need to get out your periodic tables. So take a moment, get out your periodic table, hit pause, and calculate the molar mass of NaCl. If you're not sure what that means, find Na on the periodic table, take that mass, and add it to the mass of chlorine. If you're ready to move on and you want me to show you the molar mass of NaCl, keep watching. Here is 1 mole because we need moles to cancel out with moles diagonally. And here's the molar mass of NaCl, 58.443 grams. This number, if you need to write a little note above here, this is 22.990 plus 35.453 grams, and that's Na's mass plus Cl's mass from the periodic table. This is the molar mass of NaCl. We are going to need molar masses only when we see grams or mass involved with the problem. Now you solve it by multiplying your numbers across the top, 1.5 times 58.443. I'm going to go ahead and ignore the 1 on the bottom because it's not going to change my calculation. And I get 87.7 grams of NaCl. That is my final answer. If you felt confused by that problem, go ahead and rewind the video and rewatch it and see if it can make sense a second or even a third time. So here's example 3. In example 3, we have a saline solution, and saline just means a salt solution, by the way. We have a salt solution containing 0.90 grams NaCl, and it's in exactly 100 milliliters of water. We're trying to calculate the molarity. In this problem, you should see a red flag. Whenever there's grams or moles involved, grams or mass involved, because that's really the same thing, we need to do some side work. Now, if we were to start off with our formula, big M over 1 equals moles over liters, and we tried to plug in as many numbers as possible, what we would find is that we're looking for molarity, so this is going to stay our X. The volume is actually given to us in milliliters. If you want to circle that milliliters, you can, but that basically tells us we need to convert it into liters by moving our decimal place over 3 times, 1, 2, 3 times, and converting milliliters into liters would look like this. We took our 100 and moved our decimal over 1, 2, 3 times. We do not see moles in this problem, and do not just substitute this 0.90 grams for moles because they don't mean the same thing. Instead, we have to do a side calculation. When we calculate the number of moles, we take the given, which is this, 0.90 grams of NaCl, and we use the molar mass of NaCl to convert it into moles. We can use the same molar mass from the previous problem because we're still talking about NaCl, but always make sure that your units cancel out diagonally when you're doing dimensional analysis side work. If we have grams in the numerator, we need grams in the denominator. So here I'm going, this time, not like the last problem, but this time I put 58.443 in the denominator because I need grams to cancel out with grams. This ratio here still represents my molar mass, so you always have to just make sure your units cancel out diagonal. It just depends what we're solving for. Now we can do the math because our units cancel out, grams cancel with grams to leave us with moles. And to type this into your calculator, you type 0.90 divided by 58.443. Our final answer is 0.0515 moles. But when we take this moles answer, we're going to now plug it in to the moles to finish off our equation because ultimately we're trying to figure out the molarity of the solution. So we plug that in. And now we can just solve for molarity. We can just divide 0.015 divided by 0.1, and that gives us 0.15 molar. You could have also done cross multiplication to say 1 times 0.015 divided by 0.1, and that also gives us the same exact answer, 0.15 molar. Finally, we have example 4. How many grams of solute are present in 562 milliliters of 0.24 molar solution of Na2SO4, which is sodium sulfate? And as we look at this problem, we should notice that we can plug in our molarity. 0.24 molar would go into the molarity position, and we also see a volume here, but the volume again is not in liters. If you want to circle that milliliters, you can, and let's take this decimal place and move it over 3 times, 1, 2, 3, to represent a liters volume. That's just a little conversion that we can convert from milliliters to liters because there are 1,000 milliliters in 1 liter. So there is the conversion there, 0.562 liters. We want to we want to solve for grams. And a red flag goes up. I don't have my little flag on this slide, but a red flag should go up, and that tells us that we're going to have to do a side conversion. So at this point, we can actually solve for moles. We can use our cross multiplication, 0.24 times 0.562 divided by 1 to give us 0.13 moles, and we're going to use this value to convert into grams. So here is our number of moles, 0.13 moles. We're going to use the molar mass of Na2SO4 to convert into grams. So take a moment, get out your periodic table, and calculate the molar mass of Na2SO4. What you would do is you would add up the mass of sodium, multiply it by 2, add it to the mass of sulfur, and add it to the mass of oxygen times 4. Take a moment to do that. And if you are ready, you would have calculated that in 1 mole of sodium sulfate, there are 142.042 grams of sodium sulfate. Remember to make sure your units cancel out diagonally. You can multiply across here, 0.13 times 142.042 grams, and that gives you a final answer of 18.5 grams of sodium sulfate.